Hello. First, I'd like to say thanks to the organizers of the Nearly Carbon Neutral Geometric Topology Conference. I'd also like to thank the organizers of our session. It's a real pleasure to be able to participate in this conference I know you all work so hard to organize. What I want to talk about today is an embedding of ribbon Higman-Thompson groups into big mapping class groups. Everything I'm going to talk about is a joint project with Xiaolei Wu at Bielefeld University. First, I want to discuss a motivating question. This question appears in the survey paper by Era Mayana and Balamis, where they ask about geometrically defined subgroups of the big mapping class group, which surject onto other interesting classes of subgroups of the homeomorphism group of the Cantor set, such as Higman-Thompson groups, Narrowing groups, etc. In this talk, I'm going to talk about the case in the Higman-Thompson groups. Our goal is to generalize the notion of asymptotic mapping class groups as introduced by Funark and Kapugian to answer this question. To start off, we're going to build some infinite type surfaces. These surfaces we're going to build using some basic building blocks. Our starting building block is just going to be a D-leg pants. We'll say a D-leg pants is a surface which is homeomorphic to a D+1 fold sphere. So you can see here, for instance, an example of a 3-leg pants. Now from a D-leg pants, we can build up an infinite type surface. We'll start with sigma, a compact oriented surface. Then we'll build up to a surface which we'll call sigma dr infinity. The way we'll start this is we'll first build sigma dr0 by just simply deleting the interior of a disk on sigma. Next, we'll build sigma dr1 by attaching to this newly formed hole an r-legged pants. So this r here is our first indexing number on my infinite type surface. My second indexing number d is going to occur from this point on, where from this point on, I'm going to start attaching d-leg pants. In other words, sigma drm+1 will be obtained from sigma drm by gluing a pair of d-leg pants to every non-base boundary circle. When I say the non-base boundary circle, I mean these new boundary components that we've produced in this procedure. The boundary components of sigma dr infinity coming from the base surface, in other words, are what we're going to call the base boundary components. So as an example here, I have the picture where I take my starting surface sigma to instead be just simply a disk. In this case, the surface I'm going to build up will instead call D33 infinity. So in this case, both R and D are equal to 3. And what this corresponds to is the fact that my base surface here is a 3-leg pants. And then additionally, all the surfaces I add going forward are also 3-leg pants. Notice that there are some additional pieces of information going on in this picture. For one thing, I have these dotted lines going down the sides, which I'm going to call the seams of my pants. I also have some loops here that are naturally occurring on my picture. So these loops are going to correspond to all the places in which we've glued a pants. So I'm going to have them on all different levels here. And I'm going to call these loops my admissible loops. Notice that what's happening with these seams is they are actually dividing my admissible loops into two halves, a front half and a back half. And they're similarly dividing all of my pants into a front pair and a front side and a back side. We'll call these front sides and these back sides the visible/invisible sides. So the front, of course, will be the visible. The back side we'll call the invisible side. And collectively, all of this information, the visible, invisible side, the admissible loops, and the seams, we're going to call all of this information the D-rigid structure on my surface. Now, from this information, we can define what we're going to call admissible subsurfaces. So we'll call a compact subsurface admissible if it contains the base surface. So remember, the base surface is just this original pair of pants. And moreover, if all of its additional boundary components are in fact admissible loops. So in other words, we need our boundary components to be various pieces here. They don't all have to be on the same level, but we just need our boundary components, our remaining boundary components here to correspond to these admissible loops. Now from this D-rigid structure that we have on our surface, we can define these asymptotic mapping class groups. More specifically, let's suppose we have two surfaces that both have D-rigid structures on them. And let's take some homeomorphism between the two surfaces. We'll say that this homeomorphism is asymptotically rigid if there exists an admissible subsurface A contained in the first surface, such that phi of A is also admissible in the second surface. Phi restricted to A maps the base boundary components to the base boundaries and the admissible loops to admissible loops. And finally, if we restrict to the portion outside of A, we get something rigid, meaning that it respects the traces of the canonical D-rigid structure, mapping the suited D-pants decomposition to a suited D-pants decomposition, mapping seams to seams, and the visible side to the visible side. If we want, we can drop this last hypothesis about the visible side to the visible side and allow it to switch the visible and invisible side, in which case we get the quasi-rigid asymptotic mapping class group. Okay, so now I claim that these asymptotic mapping class groups have connections to the Higman-Thompson groups. So now I want to step aside from the world of mapping class groups for a short time and instead define for you Thompson's groups. So I'm going to start by defining Thompson's group V, and then I'll tell you how that generalizes to the Higman-Thompson groups. Just some history first. The Thompson groups F, T, and V first appeared in 1965 in some handwritten, unpublished notes written up by Richard Thompson. As it turned out, T and V were the first examples of infinite and finitely presented simple groups. V is going to be the one that's of interest to us here. Higman generalized V in the 70s, a little bit later, to an infinite family of finitely presented, virtually simple groups. So these groups, again, have two indexing sets, just as before. There'll be D and R, where D has to be at least 2 and R needs to be at least 1. So we'll call these groups VDR. I'm going to define these groups in two different ways that are both going to be useful to us as we consider this. So these are going to be groups of homeomorphisms of the Cantor set. So first, let me discuss the Cantor set just a moment. Let's take the Cantor set to be the infinite sequences of zeros and ones. We'll take them to be the right infinite sequences here. Then what we can do is we can consider a finite sequence of zeros and ones, and this will give for us something called the cone. So we'll say the cone at the finite sequence of zeros and ones will be all of the elements in my Cantor set that have that finite sequence as a prefix. The set of cones form a clopen basis for the topology on the Cantor set. The way to think about this is if you think about all the things that begin with 0, this is giving you the left half of the Cantor set, whereas all the things that begin with 1 give you the right half. And so on and so forth. You can subdivide the Cantor set into smaller and smaller chunks by taking various lengths of finite sequences. Then using these cones, we can define something that we call a prefix replacement map. So what we're going to do is we're going to consider two partitions of the Cantor set into cones. Let's call the first partition U1 through UT and the second partition V1 through VT. Then the prefix replacement map is just a map that takes anything with the prefix UI and replaces the prefix UI with the prefix VI. So what this is doing to the Cantor set is it's taking my chunks, it's shuffling them around, and it's stretching and compressing them before putting them back together into a single Cantor set. The set of all prefix replacement maps is then what we usually call Thompson's group V. V is often thought of as being some sort of infinite version of a finite symmetric group. It shares many properties with finite symmetric groups, but it's acting on this infinite set of the Cantor set. There's an alternate definition for Thompson's group V that involves something called strand diagrams. The strand diagram definition is going to be slightly more useful to us here in the setting as we want to convert back and forth between mapping class groups. So instead of giving the formal definition using the strand diagrams, I'm just going to do an example that will illustrate how this works. So let's start with a specific prefix replacement map. Let's take the prefix replacement map that takes the cone 0, 0 and maps it to 1, 0. And let's say it takes 0, 1 and maps it to 0. And finally, it takes 1 and maps it to 1, 1. So the way we can build a strand diagram that represents this homeomorphism in the counter set is we're going to draw two finite binary trees. My top tree is going to be the one that corresponds to my domain. So in other words, I want this tree to have leaves that are represented by the numbers 0, 0, 0, 1, and 1. So that tells me I should have a picture like this: 0, 0, 0, 1, and 1. And then I'm going to build a matching tree, but upside down, that corresponds to my codomain. So my codomain has 3 leaves as well. It says I should have leaves 1, 0, 0, and 1, 1. So I have a tree that looks like this: 0, 1, 0, and 1, 1. And now all I have to do is I just connect using strands these the various leaves here. So 0, 0 gets mapped to 1, 0. So I draw a connector here. 0, 1 gets mapped to 0. So I draw a connector here. And 1 gets mapped to 1, 1. So I just draw a connector here. The problem is we have to be a little bit careful when we think about these strand diagrams, because strand diagrams don't uniquely represent elements of Thompson's group. So as an example, what you can think about is the fact that I can break my cone into 2 pieces, so say a left half and a right half. And I can break my codomain 1 similarly into its left half and right half. And I can just connect the left to the left and the right to the right, and this defines the same homeomorphism as the Cantor set. What this does in terms of my strand diagram is it corresponds to putting an extra break point here on the right side and just connecting up these 2 pieces. And so when I talk about this alternate version of Thompson's group V, I want to define V as equivalence classes of strand diagrams, where the equivalence relation is the one generated by the splitting. Now, to generalize from Thompson's group V to the Higman-Thompson's group VDR, all we have to do is replace our domain tree and our codomain tree with instead a set of R trees, so R many trees, and each of our trees are going to be D array trees. So just as an example here, I have a picture of an element that's contained in Thompson's group V32. So V32 here, what this is it's going to be, so what you can see here in this picture is I have 2 domain trees and 2 codomain trees. And my domain trees are both 3 array trees and my codomain trees are both 3 array trees. And then I'm allowed to connect up the leaves in any way in which I want. I can think about the way I'm connecting these as permutations of the leaves. Remember, we often want to think about Thompson's group V as being an analog of a finite symmetric group. So we really want to think about these as permutations. But now, as we generalize the Higman-Thompson groups to the ribbon Higman-Thompson groups, all we have to do here is to replace the permutations by ribbons. So in other words, we're going to think about these as flat ribbons that can twist and twist around each other. And in this way, the splitting operation that we had before, this operation of adding this extra caret, it's going to correspond to something like this. So if I have a twisted ribbon, when I slice it down the middle, you can imagine what a ribbon will do if you slice it down the middle like that. It will twist, the individual pieces will twist, and then they will also twist around each other. So this is the new equivalence generating relation that we need here, is this operation of splitting a ribbon into 2 pieces. We can sometimes require the ribbons to maintain their orientation. So what I mean by that is we maybe will expect that the ribbon begins with the front facing and ends with the front facing. And if that's the case, then we're going to call the group not just the ribbon Higman-Thompson group, but we'll call it the oriented ribbon Higman-Thompson group. So the first thing I proved with Chalet is that we were able to show that in the case of the disk model, when we build this infinite type surface, the asymptotic mapping class group is isomorphic to the oriented ribbon Higman-Thompson group. And the quasi-rigid asymptotic mapping class group, remember, this is the one that allows us to switch the visible and invisible sides. This is going to be isomorphic to just the ribbon Higman-Thompson groups. In both cases, these groups are dense in the big mapping class group. Just to kind of show you how this works, it's not so hard to see. But what we can do here is we can think about having 3 ternary trees here that we're doing something to. And then the way we actually, what we can do is we can take the 3 ternary trees that are showing up in the Higman-Thompson group, and we can just artificially add in a single root that connects them all up. And using this analogy, you can sort of see why these 2 groups should be actually isomorphic to each other. One of the benefits of having this geometric model for the Higman-Thompson groups is it allows us to prove something called homological stability. Let me remind you a little bit about what homological stability means. So let's suppose you have a family of groups, one that embeds into the next. So here we have G1 embedding into G2, et cetera, et cetera. And we say that these groups, the sequence of groups, satisfies homological stability if the induced maps on homology are isomorphisms in some range that increases within. Examples of groups that, classical examples of groups that are known to satisfy homological stability include symmetric groups, proved by Nakaka in 1961, general linear groups proved by van der Kollen in 1980, mapping class groups of surfaces proved by Harrer in 1985, and Higman-Thompson groups proved by Sismic and Wall in 2019. What's cool about Sismic and Wall's work is that they use this to ultimately show, moreover, that Thompson's group V is actually acyclic, which answered the question of Brown's from 1989. So what we did is we extended this work of Sismic and Wall to the ribbon Higman-Thompson groups and the oriented ribbon Higman-Thompson groups. So what we showed here is that the inclusion maps, where what we're doing here, our inclusion map is just to increase the number of roots that we have on our trees. So the number of trees we're working with just increases. That this embedding, the sequence of groups, satisfies homological stability. What's great about this is that these groups, one of the things Chalet and I were able to show as well, is that these groups are also dense in the big mapping class groups. So I believe this is maybe the first homological stability result for a dense subgroup of the big mapping class group. Our main technique here was to apply a general categorical framework that was developed by Randall Williams and Wall. Without getting into too much detail, I'll just say that it produces a category. Yeah, so without getting into too much detail here, let me just say that what ends up happening after you run their construction is you produce some object in which your group is acting, and you want to prove that this thing is sufficiently well connected. So in our case, the thing that becomes the thing that our groups act on is something called the lollipop complex. So what we're going to do, let me define here in the last couple minutes of my talk here what I mean by a lollipop. So what we're going to do is we're going to take the interval from 0 to 2 where we identify the number 1 and 2. So what this is a lollipop. Okay, it's going to be an interval with a loop attached to the end. And we're going to have some fixed, with our fixed base point 0. And so an injective continuous map from this 0 to 2 interval where 1 is identified with 2 into our infinite type surface is called a lollipop on the surface if, when I restrict alpha to the portion of the interval 1 to 2, that is going to be isotopic to one of our admissible loops. And the first part of our lollipop, the 0 to 1, is an arc just connecting the base point on the outside of my disk to the loop for the interval 1 to 2. Then, just like in many of the other complexes studied in the world of big mapping class groups, we'll say a set of K lollipops, we'll say a set of K plus 1 lollipops forms a K simplex if they're pairwise disjoint. So here I have sort of a picture of 2 lollipops in my picture. So I have this fixed base point on the boundary of my disk, and then I have these maps. So here's my map. Here's the portion of 0 to 1. Here's the portion of 1 to 2 wrapping around my admissible loop here. And so what we were able to prove then is that the lollipop complex is contractible, and the consequence of the contractibility of this lollipop complex is ultimately that we get the homological stability result. All right, and with that, I'm sure I am out of time, so let me just end by saying thank you again.